It's Paul back with the second snow day lecture from February 9th. This one is much shorter and simpler. I'm going to show you how to solve second-order linear differential equations when the coefficient functions p and q are not quite as well behaved. This happens all too frequently, particularly in equations that arise when you try to solve physics problems. The functions p of x and q of x are not analytic. They don't have a power series expansion, but the coefficient of y prime can be written as an analytic function divided by x, and the coefficient of y as an analytic function q of x divided by x squared. Under these circumstances, the equation is said to have a regular singular point at x equals 0. This is a very standard topic in differential equations, and I'm surprised that although Holland mentions this case, he leaves out the very easy proof that these equations can be solved. Here's the trick. Instead of looking for a power series solution where the terms involve x to the 0, x to the 1, x squared, and so on, we'll look for a solution where the first term is x to the k, the second term involves x to the k plus 1, and so on. K is not necessarily an integer. It's not necessarily even real. And if k is a negative number or not an integer, then the function y of x is not analytic at x equals 0. If k is a positive integer, then y is analytic. It's just the first few terms are missing. So let's write our equation out. I'm going to multiply through by x squared and write it as x squared y double prime plus xp of x times y prime plus q of x times y equals 0. And now let's ask ourselves, for what value of k is the coefficient of the first term in the solution going to equal 0? Let's get to work on this. So, y of x is x to the k times the standard power series. In other words, it's y naught times x to the k plus y1 times x to the k plus 1 times more terms. When we differentiate that, differentiating this term gives k y0 x to the k minus 1. Differentiating this term gives k plus 1 times y1 x to the k. We get more and more terms, but in fact only the first one's going to matter. So for y double prime, the first term is obtained by differentiating this term. Of course, we get k times k minus 1 times y0 to the times x to the k minus 2 plus some more terms. Now let's substitute into the equation. P of x is an analytic function, so I can write it as p naught plus p1x plus more terms. Similarly, q of x is q naught plus q1x plus more terms. And when we substitute into our original equation, x squared y double prime turns into k times k minus 1 times y0 times x to the k. Remember, we multiplied by x squared. The second term has x times p naught. The p1x will give us higher powers of x, which we don't care about. So we've got p naught times k times y0 times x to the k. Again, this x to the k minus 1 got multiplied by x and turned into x to the k. There are more terms that don't matter. Finally, let's look at the term involving y of x. We multiply by q naught plus q1x plus more terms. We multiply that by y naught x to the k plus more terms, but the only term that matters for us is q naught y naught times x to the k. And when we add all these things together, we get 0, and therefore the coefficient of x to the k has to equal 0. What is that coefficient? It's k times k minus 1, which is k squared minus k, plus p naught k plus q naught. All these things get multiplied by y naught, but that cancels out. So here's a really simple quadratic equation. K squared plus p naught minus 1 times k plus q naught equals 0. This is called the Indicial Equation, and since the technique was invented by the German mathematician Frobenius in the 19th century, you can say this is the method of Frobenius. I suppose you can even call this equation the Frobenius Indicial Equation. It's guaranteed to give you at least one value of k that leads to a solution for the equation. Now here's the whole story on this equation. If you get two real roots that don't differ by an integer, they give two independent solutions. If you get two complex roots, each of those will lead to a solution, or you use just one of them and take the real and imaginary parts. If the quadratic has a double root, we find only one value of k that works, and we've got to search elsewhere for a second solution, but Abel's method will give us a second solution once we have one solution plus the Wronskian. The tricky case is the case where the roots differ by an integer. In that case, the larger of the two roots always gives a solution. Sometimes the smaller one doesn't give an independent solution. Let's look at a really simple example of this. Here's an equation with a regular singular point. X squared times y double prime minus 6y equals 0. Singular because the term in y double prime is multiplied by x squared. Well, there's no term in y prime in this equation, so p of x equals 0 and p naught is equal to 0. What's multiplying y is just a constant, so q naught is equal to minus 6. And the indicial equation turns into k squared minus k because p naught was 0, minus 6 because q naught is minus 6, and this factors very neatly into k minus 3 times k plus 2 equals 0. So the two values are k equals plus 3, k equals minus 2. The larger of these two roots is guaranteed to work. Let's check it. When I plug x cubed into this equation, I get x squared times the second derivative of x cubed, which is 6x, minus 6 times y, which is x cubed, and that indeed equals 0. The smaller root, k equals minus 2, is not guaranteed in general to work, but in this case it does. If I try y equals x to the minus 2, I get x squared times the second derivative of x to the minus 2. That's minus 2 times minus 3 over x to the fourth. And when I subtract 6 over x squared from that, I get 0. So we found both solutions to these equations, to this equation. Warning, this lends itself very nicely to inventing multiple choice questions to put on quizzes. So be sure that you can apply this method. It may get you a question right really quickly at some point. And we are done.